Dr. Richard Lindzen's next.
Okay. Well, let's see if I can see my slides. Yeah. Okay. The title is a little bit excessive, but it describes what I'm going to talk about, which is what I think climate is really doing, why I fear it doesn't matter with respect to policy, and why I think that matters might still turn around. Does this work? Yeah. Okay, here is a graph. Many of you may not have seen it. It's a simple graph John Christie and I put together. The vertical axis is temperature, degrees centigrade, and the horizontal axis is just various kinds of climate change that people know how to handle. Of course, these vary from place to place, and we've taken it from various cities in the US, all over the US, Seattle, Boston, so on. And at the far left, what you have, I don't know, no, I can't use a pointer. At any rate, is the warming we've seen over the past 120 years. And that's barely budging off the bottom. And then we go to things like, from 8 a.m. to 10 a.m., and from sunrise to afternoon, and so on. And of course, it's increasing to very large amounts. And we deal with all of those. So a question arises, and the question is the following. How is it that the small seeming change in global mean temperature anomaly is taken to imply major climate change? And people don't deal with it. I notice even at this meeting, we bloviate about 2 degrees or 1.1 degrees and so on, and never deal with the fact we're dealing with something tiny. That shouldn't be a problem. Well, let's consider. The answer, especially with Sherwood's use of paleoclimate, is something called polar amplification. The idea here is that the mean temperature change, for instance, during the Ice Age or during the Eocene, was around 5 degrees. And, if 5 degrees in the change in the mean can be such remarkable change as a major ice age or the so-called climate optimum of the Eocene, then we better worry about small changes in sensitivity if they start approaching that. But where did this notion of polar amplification come from? And again, nobody is dealing with that here, but it turns out to be a crucial idea. It comes from paleo data, and that's what I've just mentioned. In paleo data, the change in the tropics to pole temperature difference, I'm referring to it here by little delta T2, is listed here. So you have these changes in the tropics to pole, 20 degrees in the Eocene, 40 degrees today, 60 degrees roughly during the glacial maximum. And they were accompanied by small changes in tropical temperature. And that has its own interesting history, and I won't dwell on it too much. The original studies of these phenomena, for instance, for the glacial maximum, actually had tropical temperatures increasing. And the original study by Shackleton and Burmsa for the Eocene had tropical temperatures decreasing. And that didn't look at all like what the climate alarmists were saying. So there's huge efforts to change it. And currently, the feeling for the Eocene by someone called Dan Schrager at Harvard is that it's the same as today. Nothing occurred. And for the glacial maximum, they've managed to squeeze out the possibility that it was also a degree cooler in the tropics. Okay, you talk about fudging data, it gets easier as you go back further, but all I'm saying is it's always small compared to this. So the idea was, this could mean that small changes cause it, but the question is, was this really polar amplification of the small and uncertain tropical temperature change? And let's look at it. This is a kind of schematic of the temperature of the Earth. The horizontal axis is sine of latitude, so it gives an area averaging. The boundary between the tropics and the extratropics at x1 corresponds roughly to x1 equals a half, which is 30 degrees latitude. And you can go to the reference there if you want to derive it, it's trivial. But the average temperature here will be T1 minus this delta T2 fraction 1 minus x1 over 2. So that'll be roughly 1/4. Okay, so there you have a simple formula. And if you apply it to major climate change, what you find is, for the delta T2 component, you get about plus or minus 5 degrees, because it's 20 degrees change in delta T2, and you get almost nothing for delta T1. What that means is, obviously, that delta T bar is dominated by the second term, the change in tropics to pole temperature difference. Fair enough. But there's another question. Do we see anything like this in the current warming episode? And the answer is no. Here is the change in the tropics to pole temperature difference over the period 1880 to 2020. And it's, it gets smaller, it gets larger, it wobbles all over the place. It has almost no bearing to the mean. Moreover, the numbers, and I can barely see the index, but if you divide them by 4, they're pretty tiny. And you can see that now by comparing the mean temperature and the tropics, the global temperature. Orange is the global. And basically, the global tracks the tropics and is generally smaller and irregular. So we're dealing with 2 different climate changes. We're calculating our climate sensitivity based on the present, which seems to have nothing to do with major climate change. This is profoundly different. What's going on? Well, what's going on, in fact, is physics. The tropics and the extratropics represent profoundly different dynamical regimes. People here in Florida, I think, probably realize the tropics are very different from the extratropics. The prevailing winds are easterly in the tropics. In the extratropics, they're westerly. The major perturbations in the extratropics are the highs and lows that we associate with weather. We don't see the same type of thing in the tropics. They're smaller. There is a large Hadley circulation in the tropics. It ends at the subtropical jet, which forms the boundary to the extratropics. At any rate, so what's determining this? Why are the 2 profound regimes there? And it is because of the rotation of the Earth. I hope most of you are familiar with the term Coriolis force. Coriolis force effectively depends on the vertical component, the component perpendicular to the surface of the rotation vector of the Earth. So that's on the right there. And in the extratropics, the component perpendicular is significant, and in the tropics, it's almost parallel to the surface and does not inhibit cross isobar flow. What does that mean? Well, we'll see that in the next slide. The pictures again. The cross isobar flow in the tropics homogenizes horizontal temperature differences. And that, you'll see, is a characteristic of the tropics. The temperature differences with latitude are minimal. It tends to be pretty homogeneous. On the other hand, where you have a Coriolis force in the extratropics, it inhibits wiping out the gradients, and we have the gradients. On the other hand, it has limits. It is due to an instability, and if you go beyond a certain point, the instability stops. And what did I just do here? I pushed the wrong button. Yeah. Okay. At any rate, so you have the cross isobar flow homogenizing the tropics. In the extratropics, you have what is called baroclinic instability, the highs and lows. And their limit, it turns out, it's a really hard calculation. It was done by colleagues Malta and Ferrari at MIT. What it determines is the slope of one of these bars. What these bars are isentropic surfaces. For those of you who know meteorology, those are surfaces in potential temperature. And baroclinic instability says that the isentrope along which transport occurs that leaves the surface at the boundary of the tropics, that isentrope has a slope, and that slope determines the polar tropopause. Okay, that's technical, but it determines the temperature difference between the tropics and the pole at the polar tropopause level, about 6 kilometers. And it sets it to about 20 degrees. That's an interesting number. That is the temperature difference during the Eocene, when we had no ice and so on. You'll notice some of these bars originate not in the tropics, but at the surface. And they have an important role as well. The ones originating at the surface allow the influence of extratropical surface conditions, including the role of ice, which produces what's called the Arctic inversion, and the influence of ocean transport. But the crucial thing is the processes that determine the temperature difference are extratropical. On the other hand, the temperatures that determine the tropics do depend on the greenhouse. And the fluxes in and out. But turning back to this, it's telling you you do not have polar amplification. On the contrary, whatever is happening in the tropics is just an additive constant to the temperature everywhere. And so if you have 1 degree, 1.5 degrees, it doesn't give you a big thing in the Arctic, it gives you 1.5 degrees. And we've been sort of screwing around and ignoring the general circulation. Without polar amplification, small warming remains small warming. And for major climate change, like the Eocene or the Ice Ages, greenhouse-based climate sensitivity is largely irrelevant. Okay, in point of fact, although this is a major problem, it's completely ignored. But, part of the reason it's ignored is virtually every aspect of warming alarm narrative is faulty. Despite this, I think it is fair to say we are losing the battle in the policy arena. I differ with Greg on this, and I'd like to ask, why are we losing this battle? And the answers are pretty obvious. The alarmists control the funding, which allows them to entrain many scientists and scientific organizations, including the American Medical Association. I mean, this is crazy. For anything we show, there will always be some so-called scientist who will claim the opposite. They've been paid to. They take advantage of the insecurity of the public to denigrate skeptic claims, because they point out if the skeptics are wrong, then the public is at severe risk. They personally have more at stake financially. And they've learned from Goebbels that a big enough lie, repeated endlessly, becomes truth. And they are more sophisticated in preserving the narrative. And let me explain that. It took me a long time to realize that. They realize the utility of overt errors. So, for instance, you point to things that have no relation, perhaps, to climate, but have the capacity to frighten people. Wildfires, extremes, obesity, autism, God knows, you'll have all of them associated with climate. And what is the implication? I think the people saying this know it's nuts. But the implication somehow is left that if they weren't misrepresented, they implied decarbonization. And so you could skip over all the logical steps that would be needed to do that and establish that if you see people getting fatter, it means you have to get rid of carbon dioxide. Keep the skeptics busy pointing to errors in things like climate sensitivity, while not questioning the narrative that the greenhouse effect determined major climate change. I'm as guilty as anyone of this. You know, you looked at the feedbacks and you said, these don't make sense, we don't know enough, and so on. And you forget that climate sensitivity calculated this way may not be the relevant thing to do. I have to give credit to Tony Heller, who quickly realized this because of a very simple thing. I mean, he was not into dynamics, but the climate of the Earth has dozens of climate regimes. How did one number correspond to sensitivity of this system to anything? The appeal to the insecurity of non-scientists is very important. A vast majority of the population cannot deal with graphs, numbers, and so on. We know this, and know it at the university from our humanities colleagues. So you appeal to their insecurity. They feel insecure about this by providing simple to understand narratives, even if they're wrong. So for example, when an Al Gore tells you CO2 is a blanket, that's a lot simpler than what I've been telling you. And its simplicity is a source of comfort to the scientifically illiterate. Okay, so where does this leave us? No. Humor is always a potent weapon, and we use that often, and I won't dwell on it much, but at MIT we have somebody who's anonymous called the Babbling Beaver. The beaver is the mascot of MIT. And he makes fun of what we're doing there. MIT is gathering our librarians to train climate catastrophists to control Wikipedia's narratives, and describes this in detail as a crazy thing MIT is doing. Some approaches defy parody. We make fun of the Medical Association, but this one I don't think you've seen. Came from a friend who is a professor of musicology, and it's a forthcoming meeting in Essen, Germany on music and climate change, artistic action in times of crisis. I could read it to you, but I don't think it would help you or me understand what the hell they're talking about. Inconsistency obviously doesn't matter. The Boston Globe, I think 2 days ago, had the following. It was describing the fact that we had a cold spell. It was really very cold, and 3 or 4 hospitals, I think 3 hospitals, had broken pipes, and they couldn't admit ambulances with emergencies. And so they were saying, here's an example of how climate is preventing healthcare. And then what do they conclude? Well, unfortunately, I have to go back. Can you go back on this? Yes. You can't see it. Somehow the slide screwed it up. Their conclusion is climate change is stealing New England's winters when they've just been talking about frozen pipes. I don't know. In any event, ordinary people do remain skeptical. For obvious reasons, the things that they're presented with are kind of nuts. The educated elite seem most vulnerable, and people have mentioned Orwell, and he did famously say there are some things so stupid that only intellectuals could believe it. And there are reasons for that. I mean, what is the good student except the person who can rationalize whatever the professor says? So. But in any event, I think people in general of goodwill do want to believe that their government is not out to get them, which may be a false wish. There follows my take on the issue from 31 years ago, and I'll read that to you. Such weak predictions feed and contribute to what I have already described as a societal instability that can cascade the most questionable suggestions of danger into major political responses with massive economic and social consequences. I've already discussed some of the reasons for this instability: the existence of large cadres of professional planners looking for work, the existence of advocacy groups looking for profitable causes, the existence of agendas in search of saleable rationales, and the ability of many industries to profit from regulation, coupled with an effective neutralization of opposition. It goes almost without saying that the dangers and costs of those economic and social consequences may be far greater than the original environmental danger. That becomes especially true when the benefits of additional knowledge are rejected and when it is forgotten that the improved technology and increased societal wealth are what allows society to deal with environmental threats most effectively. The control of societal instability may very well be the real challenge facing us. This was 1992. Well, we're now in 2023. We failed to control the societal instability. However, the pain, the evil, and evident uselessness associated with the proposed policies seems to be turning the tide. After all, normal people will, one hopes, want a second opinion before being forced to suffer, especially if the suffering serves no environmental purpose, regardless of what one thinks about climate. Thank you.